Hey guys, this video is going to be about TXVs and pistons. Now we've all had talks about which one is better, TXVs and pistons, and we could go on to no end about, TXVs are necessary in certain situations when you have multiple stages of cooling and heating. Pistons are typically used in single stage, of course, lower SEER applications. Not quite as efficient as pistons. Pistons can change their capabilities with changes in load. Fixed orifice or piston is usually, it's fixed. You can't change it. There used to be adjustable sort of fixed orifices, but they're not really used anymore. So we really have either pistons or TXVs or electronic versions of TXVs. So those are usually the three choices that we get. So we're going to take a look. Here's a couple different kinds of pistons. We can see them on the screen here. The first you have is a Goodman style piston. I'm sure there's a technical name for it, and one of you might know it, but I just kind of separate pistons into two groups. We have the Goodman style, and the other one I do have a name for. It's called the bullet piston, is what I call it. Something where you would see it in a York application or a Nordine application, and there's a few more. Most of them use either or. Some manufacturers don't use pistons at all anymore. I don't think Trane has a single piston coil or air handler anymore. I don't think Rheem does. Goodman still has the ARUF that has a piston in it. The Nordine ones still have a piston in their 13 SEER. I don't know if they're using, I know they have an air handler with a PSC motor and a TXV. That might be their 14 SEER air handler, but their 13 still had a piston in them, a bullet style. You don't see them as much anymore, which is a shame because they're very reliable. That's sort of their MO. You never have pistons failing for the most part, although I've gotten a few pictures from some of my subscribers about pistons that have failed due to the Copeland rust inhibitor issue. But typically they don't fail. They should be there for the life of the unit. I have a lot of information I put together. I chose to look at piston and TXV performance in Wilmington, North Carolina, which is where I live, and across in Las Vegas, Nevada, because they're sort of opposite environments. I want somewhere with lots of heat, lots of energy in the air, and both of those locations have that. Las Vegas has more sensible heat in the air but very low relative humidity. Wilmington has a good bit of heat in the air and has a very high relative humidity. So there's quite a difference in how you would go about doing your superheat calculations, what kind of superheat would be produced by a fixed orifice under certain conditions. Because your TXV is going to want to hold a certain superheat as long as it's under its design load or close to its design load. If you go too great or too low, of course it can't handle it, but a TXV is designed to give you a certain amount of superheat back. Fixed orifice will give you whatever superheat will be produced based on the conditions, so it'll change. We're going to take a look at some documentation that I've prepared. I'm going to show you a few sections of it, and I'm going to talk along as we look at it. The first thing we're going to look at is the Las Vegas numbers that I chose. I just took weather information for one day in Las Vegas. It would have been a couple weeks ago because I've been working on this for a while. And as you see, we have our 6 a.m. through 2 a.m. temperatures. At 6 a.m. we had a temperature of 77 with a low relative humidity of 31%. As you go throughout the day, you can see at 10 o'clock it went to 89 and 97 at 3 o'clock, back down to 93 and to 82 at 2 a.m. So a relatively warm day. I'm sure Vegas has warmer days than that, but it's a good example of a nice hot day with low relative humidity. As you can see, the relative humidity dropped to 17% and rose to a grand high level of 31%. So very low. To the right, you will see two design conditions. Superheat at 75 degrees indoor and 40% relative humidity, and superheat at 75 degrees indoor at 55% relative humidity. Now what I did was I used my target superheat calculation to get superheats at the temperatures listed to the left at those times of day based on those inside conditions. And as you can see, you take all those averaging up. You see the 40% indoor conditions because Vegas is a dry place, so I'm assuming we get to have some dry indoor conditions some of the time. What I did was I did the comfort zone, which is 55% relative humidity on the right, and a more drier zone on the left. So you have superheats ranging from 11.5 all the way down to 1.5 at 3 p.m. for the 40% indoor humidity. You have 55% relative indoor humidity. We have 17.5 all the way down to 7.5. As you see at the bottom are the averages. An average of target superheat of 6.2 at 40% indoor humidity, and an average target of 12.2 at 55%. What does that tell us? Well, if we look at the target superheats for those ranges, if you have a 40% indoor relative humidity in your home in Las Vegas with those high outdoor temperatures, your superheat at certain parts of the day could theoretically reach a flooded condition in your evaporator, because the indoor relative humidity in wet bulb is so low, the load is so low on the coil, temperature outside is so high, it has pressed that condenser running pressure up so high that we're getting almost a 0-degree superheat. So it would be reasonable to say that if you were in Las Vegas in a dry home, that a TXV would be a nice thing just to keep your coil from flooding. What does that mean? It's going to keep your coil from flooding by backing off the pressure, raising the superheat, but in turn you may have a little bit lower operating pressure, you may have a little bit higher compressor compression ratio. What does that mean? Just like your Copeland rust inhibitor issue, what happens is it blocks the TXV with that additive they've used, and you have a high head pressure and low back pressure. Now compressors don't really like it when they have a high compression ratio of over about 4:1 at least. So imagine 4:1's 280 over 70, and the compression ratio is measured in absolute pressure, not gauge pressure. So you add about, at sea level, you add about 15 psi to get your compression ratio. And what that means is, if you're at sea level and you had a compressor running at 280 over 70 gauge pressure, you would add 15 pounds to that to get the absolute pressure, meaning you would have 295 over 85. And as you went up in altitude, that would change, and you have to consult a chart, which we will be looking at that chart later for converting standard CFM to actual CFM. But for right now, we're just going to sort of touch on it just briefly, because it does make a difference when you're gauging what the compressor compression ratio is, because you don't want it to be too high or you'll have difficulty in the compressor staying lubricated, especially in a piston compressor, and it could shorten the life of your compressor. So there's some give and take there. You say, why you don't want your evaporator to be flooded and have flood back to the compressor, you also don't want to wrench back the pressure so far that you have an issue with the lubrication of the compressor. So as you see, you can go either way with that. There's pros and cons to using TXVs and pistons in that situation. If you move over to the superheat at 55% indoor relative humidity, it's much more favorable. You have a 12.2 average target superheat with a piston. If that is your target superheat and it ranges from 7.5 to 17.5, I don't see a big disadvantage to the piston. The biggest disadvantage I could imagine would be that TXV is better at changing loads, but there's not an extreme change in loads there. There's not a lot of latent heat in the air. In fact, if we go all the way to the right hand side, that is your outside air enthalpy. Enthalpy is something we're going to talk about a little bit more. Just imagine it's like the sum total of the heat energy in the air. Just think of it that way. Totaling up the sensible and latent heat. As you see, Las Vegas this particular day, at the bottom you can see a 28.476 average enthalpy, which is not extremely high. So that's not extremely high at all. Alright, we're going to look down at Wilmington, North Carolina numbers. Now we have the same numbers, 6 a.m. to 2 a.m. It's a little bit different. This particular day, as you see, the high was around 80 that day. So we have temperatures ranging from 72 to 79 on our chart. The real difference is, besides the much cooler temperatures, is the much higher humidity level in the air. It ranges from 79 to 95%. And it may sound insane, but it's very typical of the southeast United States. Places like North Carolina, South Carolina, Georgia, Florida, the Gulf Coast. Guys like Ralph, Joe Shearer, John Israel could attest to the level of humidity in the air. Go to the other side of the chart and look at the outside air enthalpy average. And remember, Vegas was 28.476. But because of the humidity, our average enthalpy, the total heat in the air, is 36.648. So when you add the relative humidity and the latent heat to the total of the sensible heat in the air, which is our temperature, you can see how much heat we have stored up. It's just an insane amount of heat with all that humidity. And this was a muggy day, so it was very muggy. Like a day like today, there's a little bit less humidity in the air, but this is definitely not uncommon in the summer months in the southeast United States. Let's look at our numbers. At 75 and 55%, we have a category, and at 75 indoors and 65%, because we're more likely to run a higher humidity in houses in the southeast because the outside air has higher humidity. Also, if your sensible numbers are down, like your 72 outside, 79 outside, then your air conditioning may actually satisfy and not do as much dehumidification as you would like. That's a good argument for a two-stage system or some sort of manipulation of the blower speed or something like that. I think Joe uses undersized systems at a longer runtime. The same theory, that you're going to dehumidify the air through one of these means. That's the reason why I used that VFD at the house down at the beach, because the humidity level was so high. We actually wanted to construct a runtime at the beginning of the cycle of just a very low blower speed, so that would just dehumidify like crazy for a while monitoring the coil to make sure it didn't freeze. Because if we didn't do that, it would just never be dehumidified unless we just undersize the system so badly that it would just run constantly. So we have 75 and 55% relative humidity and 75 and 65% relative humidity. You see our average superheat on the ideal conditions, with this 55% relative humidity, that's comfort conditions, is 18. So we range from 16.5 to 20 degrees target superheat, which is not too bad. There's a lot of TXVs that fall right in that range. So that's not too far off from just, you could use a piston in that situation. The load's not swinging a whole lot. Now you will have changes in load, which the TXV is better at, but in that instance the piston seems to perform in a similar way to the TXV as far as target superheats matched up throughout this particular day. But if we go up to the 65% relative humidity, our target superheats going to climb above the level where a typical TXV would go. You don't see typical TXVs running 25 degree superheats unless there's something wrong or you have a Copeland compressor. Haha. 24.5 down to 21, back up to 22 to 23.5. So an average target superheat of 22.5 degrees. So a little bit higher. Somewhere where you might say, well, I'd rather have a TXV to dehumidify this air. Now, if you're going to manipulate the blower speed, I would put a TXV on that machine because you're changing the load drastically, and you want your TXV to be able to adjust so you don't flood back when you're dumping that blower speed down real low. And as you can see on the far right is the outside air enthalpy, like we were talking about. It's so much higher because of all that latent heat. So as you can see from the first two cities that we're looking at, or the only two, you can see arguments for using pistons and TXVs and which one is better. I mean, piston, superheat, if you're getting a superheat target during the day between 10 and 20, or even a little bit less than 10 with your pistons, then that's not a drastic difference from your TXV. One way that would open up the difference is if you change set points throughout the day. Let's say you came in, instead of having 75 and 55, let's say when you were going to work you put it on 82, and when you come home you put it on 72. Well, a TXV is going to be much better at dealing with that load, because that high initial target superheat, when you come back, the TXV will recognize that through, it takes a bulb pressure, has refrigerant in the bulb, your line's very warm, coming out because you have a high, your evaporator suction lines, very warm coming out because you have a high target superheat. So what it does is that warm suction line heats the refrigerant in the TXV bowl, opens the TXV valve, and lets more refrigerant through to bring that temperature down until it regulates that superheat. That way you don't have an evaporator that's starved for refrigerant because the superheat's so high, it's boiling off so early in the evaporator, it's not as efficient. So let's revisit some of our points here. TXV superheats typically between about 8 and 20 degrees Fahrenheit. That's the normal range that I've seen throughout the years. I don't know what they say from the manufacturer, but I'm talking about what I see in the field. I see them ranging on the low end, which is a lot of Goodman TXVs are on the low end, 7 to 9 degrees, subcooling 7 to 9 degrees, superheat, all the way up to a lot of Train stuff that I've seen over the years. It seems to come in around 17 or 18 degrees down there at the total superheat measuring point near the condenser. So anywhere between 8 and 20 I think is acceptable. When you get up into the 20s, you might start thinking something's wrong, or your TXVs just, and they can get worn out. They get just plain worn out over the years. Of course, some of them are adjustable. The Goodman TXVs they give to add on to, like the ARUF, the old ASUF, ASPF air handlers. The F at the end is flow rater, so you would take out the flow rater, which is a piston, and put in a TXV if you wanted to get that added efficiency. TXVs change for different loads. Like I said, if you change set points or there's drastic changes in weather, TXV will adjust more rapidly than a piston, because a piston has no adjustment. It just basically is just sort of like a dumb metering device. It doesn't change at all. Whereas TXV is dynamic. It can change. Whenever you change a set point, it'll react quickly to allow more or less refrigerant into the coil as needed. On two-stage systems, you're going to have only a TXV, because that one metering device is needed for both levels of refrigerant flow. You either have a mechanical TXV or electronic expansion valve. We're going to look at this AHRI matchup with the Goodman system, a 3-ton GSZ system. Now I have one with and without the TXV. It's a CHPF, which is a horizontal coil, 3743, which is, it would cover 3 to 3.5 ton machines depending on how they matched it up. And C chassis I think is the 21 by 21. Some of you Goodman guys can help me out with that. And we have that coming in at 14 seer when matched up with this GSZ 14 unit, 3 tons. So it comes in at 14 seer, but if you add the TXV to it, it comes in at 14.5 seer. So the TXV does add a little bit of efficiency. Is it a lot of efficiency? No. You have to factor in the fact that pistons don't typically go bad unless there's another part of the system that's causing them to become clogged. Pistons don't go bad, but TXVs certainly do. They lose bulb pressure, they wear out. Keeping in mind these are the valves that are opening and shutting all the time for years on end. There's parts of them that can wear out. Even the adjustment can wear out on some of the adjustable TXVs, as I've found. And sometimes it doesn't take that long for that to happen. And if you check your TXV, you might find that one day you go out there for a preventive maintenance and all of a sudden it's running a 27 degree superheat. It's still cooling, not cooling as well, but sort of like a silent loss of efficiency. It'll still cool, it'll run a little bit longer, just not be quite as good. And it's just hard to tell unless you're looking for it or having your machine serviced. That's one of the reasons why having your machine serviced is so important, because you won't find out about these things unless you do that. And there'll be silent things that go on for years and years and eventually can cause other problems in your system. We look down here at a house. It's sort of one of those energy calculators. In 4 years, with that change of efficiency, $150. In 7 years, is about $300. But these are estimates, that's why it's not exactly, 300 is double of 150, so it's a rounding of those numbers. Now imagine $300 in 7 years. If your TXV goes bad, it's going to cost more than that to replace. Under warranty, it may be pretty close to that 7-year mark, but it's only going to take one replacement to kind of erase all the savings you had. So, what's the conclusion? What is the conclusion? Which one is better? You could actually use either one of those. TXVs are the way of the future. All modern machines are going to be TXVs eventually, because you have to get a TXV to get that little bit of efficiency you need, just like ECM motors. The simple ways are going away, and the more complicated means, when TXVs aren't complicated or new. I mean, they've been around for a long time. But machines are generally more complicated. It's definitely more complicated than a piston. As you can see, there are certain environments where we could use a piston. And when you're able to use a piston, I like to use one. If it's normal operating conditions, you don't have any crazy swings in load that people are changing their set points wildly on the thermostat, you're going to leave it on 75 all the live long day, I like a piston. A piston's a good thing to have. If you have a TXV, you're going to have that benefit of a little bit extra efficiency, a little bit extra capability, and sometimes capacity. There's been slight changes in capacity when adding a TXV. Not dramatic, but a little bit. But you're also going to run that risk if it fails. You're going to have to pay for it. You're going to erase some of your savings. So it goes by case. On extremely dry environments inside, like the Vegas environment, a piston is going to have a flooded evaporator coil and doesn't make much sense there. As well as on extremely humid environments, like some of our muggy East Coast, Southern Coast, Gulf Coast days, a piston's not going to be as good as a TXV. It's just not going to measure up. But its simplicity appeals to a lot of people and appeals to me. I realize that TXVs are in a lot of the machines I put in, and most of the time it ends up just fine. But I always know that when a TXV goes in, there's going to be a chance I'm going to be changing out in the future. And I change quite a few of them every year. I don't know how many it is, but it's at least several every summer that I'm changing out. Sometimes quite a bit. I've lost count over the years. But there was some information for you guys. You could think about metering devices, how they react to temperature swings, what are the benefits of them. If you can keep your system simple, that's what I like to do. But TXVs are in even some of the simpler machines, like the thermal zones I put in were TXV. All the ICP and Bryant stuff is now TXV. So a lot of times you don't have a choice. But I like a good old piston. I like the simplicity of it. I hope you guys got a little bit out of this. Ask any questions you want to. Maybe we'll do a follow-up video if I missed anything. I'm sure there's more ways we could experiment between these two devices. So let me know. I hope you enjoyed it, and I'll see you guys on the next one.